Hi there, and welcome back to the exploration of space. To start out this new chapter on interplanetary travel, we want to present a few relevant and interesting facts. In 1977, two unprecedented events took place. The Voyager 1 and Voyager 2 probes were sent to Jupiter and Saturn. In addition to their scientific goals, the Voyagers carried a high-density record of life on Earth. This message in a bottle was introduced by the Secretary General of the United Nations. He said, "I send greetings on behalf of the people of our planet. We step out of our solar system into the universe seeking only peace and friendship, to teach if we are called upon, to be taught if we are fortunate." That's some pretty heavy stuff, and it was based on two assumptions. The first, that we'll discuss today, is that we can get from one planet to another. The second, that there may be someone out there who will want to learn about us as a planet. Here you can see the two Voyager spacecraft we just mentioned. So today, we're going to talk about planning for interplanetary travel, which starts with probes like the Voyagers, planning a trip through the solar system, which might be possible using the Hohmann transfer method we learned about in the last section, and interplanetary coordinate systems. Let's say you were planning a trip to another state. You'd get a national road map. If you were going overseas, you'd get a world atlas. And if you were planning a space mission around Earth, you could use what you know about orbits and trajectories and even use the Hohmann transfer that we talked about in the last chapter. But if you're planning a trip from Earth to Mars, for example, we have to expand our point of view to consider the entire solar system. You'll remember that the Hohmann transfer showed us how to transfer between two orbits around the same central body, such as Earth. Well, interplanetary transfer just extends the Hohmann transfer. But keep in mind that the Sun is now the central body, not the Earth. And the departure and destination planets may include Earth and Mars, or Jupiter, for example. This material may sound complicated, but we're going to break down all the information into manageable parts. So pay close attention and you'll be amazed at how much you can learn. When we described the motion for a spacecraft in orbit around Earth, we made some basic assumptions. One was that there are only two bodies, the spacecraft and a perfect spherical Earth. The other was that Earth's gravitational pull is the only force acting on the spacecraft. We ignored gravity from all the other planets, our moon, and the sun as well. We also developed a convenient coordinate system called the geocentric equatorial coordinate system that we could use for orbits around Earth. If you recall, geocentric means Earth-centered, and the second word, equatorial, told us where the fundamental plane or basic reference was located. When we decide to travel into the solar system and beyond, two things will change. Once our spacecraft gets far, far away from Earth, the gravity of the Sun becomes much greater than the gravity of Earth. So we end up using the gravity of the Sun for all of our orbit calculations. It is important to remember that the basics have not changed. Once our spacecraft is under the influence of the Sun's gravity, the spacecraft will simply fall around the Sun, just like it did around Earth. If the Sun is the central body around which our spacecraft orbits, we need a new coordinate system to keep things straight. So we introduced the heliocentric elliptic coordinate system. We can dissect this name to figure out what it means. Heliocentric means sun-centered, so the Sun is the center of this new coordinate system. The ecliptic is similar to, but not exactly like Earth's equator. If we remember that geostationary spacecraft all orbited around the equator, you can stretch that idea to include the planets orbiting around the Sun. In general, the planets in our solar system all fall around the Sun in basically the same orbit plane, and we call this plane the ecliptic. We'll look at a diagram on the next slide. But you may be asking yourself, is Earth itself falling? Well, yes, we are falling around the Sun at about 18 miles per second, or 65,000 miles per hour, so hold on to your seats. Now we can do a quick recap. The center of our heliocentric coordinate frame is the Sun. The ecliptic is the fundamental plane, and another way to define this fundamental plane is that it is the plane of Earth's orbit around the Sun. Next, we need a main direction that's fixed with respect to the universe, and we'll call it the I-axis, shown here pointing to the constellation Aries. Now that the basic plane and main direction are chosen, we set the second axis on the ecliptic plane 90 degrees from the first axis in the direction of Earth's motion, shown here as the J-axis. Finally, the last, or K-axis, is perpendicular to the ecliptic plane, so it completes the right-handed system. Now we can apply any trajectory from Earth to another planet, or even to the edge of the solar system, to this heliocentric ecliptic coordinate system. When we discussed Earth orbits, we restricted ourselves to the two-body problem, where we limited the gravity force acting on the spacecraft to Earth's gravity, hence the two-body problem. But in this simplified diagram, what gravity forces can affect the orbit of the spacecraft? You'd be right if you said that the spacecraft must begin its mission under the influence of Earth's gravity. But for interplanetary spacecraft, we have 4 bodies involved instead of just 2 like we had for Earth orbits. In order to figure exactly what the spacecraft orbit will look like, we have to consider all 4 bodies: the Sun, the departure planet, which is often Earth, the target planet, which could be Mars, and the spacecraft. We'd need some really smart people like you to figure this out. All right, let's review a few concepts here. If you study the diagram closely, you'll note that it is very similar to a diagram you saw when we discussed Hohmann transfers. We have a central body, the Sun, not Earth. And we have Earth in a smaller orbit around the Sun, and a target planet, like Mars, that's in a larger orbit. The same concepts apply here. If we want to go from a smaller orbit to a larger orbit, what do we need to do? Right, we must add energy, just like we did earlier for Earth orbits. But we still have 4 bodies to consider, not just 2. There are a lot of forces to consider when a spacecraft is traveling from one planet to another. So in order to work out the effects from all these gravitational forces acting at once, we'd have what's called a 4-body problem. This is a very challenging problem, so we'll need to find a way to tackle it without hurting our brains. Just like many of the personal or academic problems we have in life, if we use a divide and conquer approach, we can split a very complicated situation or problem into several easier problems to solve. The Earth's 2-body problem was much more manageable, as we showed in Chapter 4 when we were dealing with the spacecraft in one planet, Earth. Now, here's the good news. You're not the only ones who think the 4-body problem is overwhelming. We're going to learn how the experts split the 4-body problem into 3 much easier 2-body problems. So, we know that the 4-body problem is going to be broken down into 3 2-body problems, but how is that done? Well, if we have 3 bodies, in this case the Sun and 2 planets, we can simplify our task by assuming that we will apply the force of gravity on the spacecraft from the body that the spacecraft is closest to, but do it separately for each body. We call this approach the patched conic approximation. Let's rephrase the definition of the patched conic approximation. The individual pieces of the spacecraft's trajectory are conic sections. These sections are actually different orbit shapes like circles, ellipses, parabolas, and hyperbolas. Now, since we introduced 2 new orbits, let's take a second and define them. For our purposes here, a parabolic trajectory has enough energy to escape or leave behind Earth's gravity. And a hyperbolic trajectory has not only enough energy to escape Earth's gravity, but to go to other planets as well. By solving one 2-body problem at a time, we patch one conic section or trajectory onto another, creating what's called the patched conic approximation. That's a lot of stuff to absorb, but now we can begin to piece things together so we can actually explore our solar system and beyond. In this figure, you can see the 3 regions associated with our patched conic approximation. The blue circle and arc represent the orbits of Earth and the target planet around the Sun, respectively. Region 1 is the Sun-centered transfer orbit from Earth to the target planet. This is basically a glorified Hohmann transfer. Region 2 is Earth departure. The dotted circle around Earth defines the sphere of influence of Earth. Now, once a spacecraft crosses this dotted line, it is considered no longer under the influence of Earth's gravity. But what gravity is now affecting the spacecraft's motion? Right, the Sun's gravity is the only force assumed to be acting on the spacecraft. Region 3 is called target planet arrival. What do you think the dotted circle means here? Right again. Within the dotted circle around the target planet, the spacecraft is under the influence of the target planet's gravity. Region 1, which is solved first, is the sun-centered or heliocentric transfer from Earth to the target planet. In this region, the sun's gravity dominates. The two-body problem is defined between the sun and the spacecraft. This orbit is patched to both of the other regions. Region 2, which we solve next, is the spacecraft's escape from Earth. The red circle around Earth represents the orbit of the spacecraft around Earth. The red arc departing from the spacecraft's Earth orbit is a hyperbolic or high-energy trajectory that can get the spacecraft to the target planet. In this region, Earth's gravity dominates. The two-body problem is between the departure planet, Earth in this case, and the spacecraft. The hyperbolic trajectory from Earth is patched to the sun-centered transfer orbit. Region 3, which is solved last, is the arrival at the target planet. In this region, the target planet's gravity dominates. The two-body problem is between the target planet and the spacecraft, and this trajectory is patched to the orbit from Region 1. I think you're starting to see the logic of how all this fits together. So now we're going to talk a little bit more about the sphere of influence, or SOI. A body's SOI is the volume around the body in which its gravity dominates. In theory, a sphere of influence is infinite. But in reality, when a spacecraft gets so far away from one body and gets close enough to another body, it has left the first one's sphere of influence. So, if the sphere of influence isn't infinite, what does the SOI size depend on? If you said the planet's mass, you'd be right. The more massive planet has a longer gravitational reach. Let's continue to think about what else might affect the planet's SOI. Remember that the sun's gravity overpowers the gravity of closer planets, so the distance of the planet from the sun is another factor in determining the SOI. The Earth's SOI is about 1 million kilometers, or 600,000 miles in radius. That's well beyond the moon's orbit, but only a small fraction of the distance from Earth to the sun. Let's think about this another way. If Earth were a baseball, its SOI would extend 78 times its radius, or 7.9 meters. Follow this example in the next slide. Again, imagine the Earth is the size of a baseball. Its SOI would extend out 7.9 meters, or 26 feet. By the way, the moon would be the size shown and would only be 3.2 meters away from Earth. Our goal in using patch conic approximations is to determine the total velocity change a spacecraft needs so it can leave an Earth orbit and get into orbit around another planet. We've just learned how to use the patch conic approximation to simplify the interactions between spacecraft, the spheres of influence for the Earth, Sun, and target planet. Now, we're going to consider an Earth-bound example to explain the concept of relative speed or velocity. Imagine that you're driving along a straight section of highway at 45 miles per hour, and a friend is following in another car going 55 miles per hour. A person standing on the side of the road sees the two cars moving at 45 miles per hour and 55 miles per hour respectively. The person standing beside the road sees you go by at 45 miles per hour, followed by your friend going 55 miles per hour. But your friend's velocity with respect to you is only 10 miles per hour. So, relative to your speed of 45 miles per hour, your friend is only going 10 miles per hour faster. They say a picture is worth 1,000 words, so let's look at this information again. When we're looking at this picture, keep in mind that the V stands for velocity or speed. You are going 45 miles per hour, and your friend is going 55 miles per hour. Jerry, the rocket scientist, is watching both of you, and he knows that relative to you, your friend's speed is only 10 miles per hour. All right, now let's make this a little more interesting. Suppose your friend throws a water balloon toward your car at 20 miles per hour. How fast do you think the balloon is going? That's right, it all depends on perspective. From your friend's perspective, the balloon appears to move ahead of her car at 20 miles per hour if we ignore air drag. From the viewpoint of Jerry, who's standing on the highway's edge, your friend's car is going 55 miles per hour, and the balloon leaves her car going 75 miles per hour. But what do you see? The balloon is moving towards you with a closing speed of 30 miles per hour. Okay, let's go to the picture again. You're in the first car traveling 45 miles per hour, and your friend in the second car is traveling 55 miles per hour, while Jerry the rocket scientist is standing on the side of the road. The speed of the balloon relative to you is 30 miles per hour. The speed of the balloon relative to your friend is 20 miles per hour, and the speed of the balloon relative to Jerry is 75 miles per hour. We're going to continue our balloon example using the patch-conic approximation. Follow along so you're sure you understand how this works. Initially, Jerry, standing by the side of the road as a stationary observer, watches your friend throw a water balloon. The observer can see that your friend's car is going 55 miles per hour, your car 45 miles per hour, and the balloon traveling from one car to the other at 75 miles per hour. The reference frame is a stationary or fixed frame at the side of the road. From your friend's viewpoint, the water balloon departs his car with a relative speed of 20 miles per hour. The reference frame in this case is centered at your friend's car. This problem relates to the patch-conic approximation in region 2, where Earth is like your friend's car and the balloon is like the spacecraft. Finally, from your perspective, the water balloon lands on your car. The balloon catches up to your car at a relative speed of 30 miles per hour. The reference frame is centered at your car. It's like the patch-conic approximation in region 3, where the target planet is similar to your car and the balloon is the spacecraft, a very low-flying spacecraft at that. So, what I'd like you to remember is that your ability to have a spacecraft travel from one planet to another depends heavily on its velocity. And the velocity the spacecraft have is relative to a particular point of reference, relative to the Sun, Earth, or target planet. Take a few minutes to answer these questions. Refer back to the diagrams in this section to make sure you understand all the terms and concepts. Ask your teacher for help if you need to reinforce the material. In the beginning of this section, we introduced the Voyager spacecraft and the Voyager Golden Record that had messages for other life forms in our solar system and universe. This is a really thought-provoking and fun exercise. Break up into discussion groups and decide what your message in a bottle would be. What message would you send to interplanetary space? Present your ideas to the class. Now we've come to the end of this section on interplanetary travel. We've had an opportunity to think about travel to other planets and begun to understand how we might use simplifying techniques like a patch-conic approximation to estimate how much velocity, and therefore propellant, to actually do interplanetary missions. Astrodynamicists and other scientists continue to figure out ways to make interplanetary space travel more possible and effective. The interplanetary superhighway is proposed here. In this section, we saw how to get to other planets using an interplanetary Hohmann transfer. Even this fuel-efficient maneuver requires a huge amount of rocket propellant, significantly driving up a mission's cost. Next, we'll look at intercontinental ballistic missiles, or ICBMs.